we already seen one type of boundary condition. That's when we enforce the values of the function to be 0 at the boundary, right? So today, let me just start by introducing a boundary condition that is very similar to what we have been discussing before. So let's consider a slightly modified boundary condition. So the differential equation is exactly the same, but the boundary condition is u0. Let's still set u0 to 0, but u1 equal to a different known value. Let's say equal to a. All right. So a is a number that we already know. So basically, what we are doing is we set the value at 1 to be not 0, but some other known quantity. In this case, let's discuss how would we modify our space for u and for v. All right. So again, we take the same basis functions. But if our u1 is equal to a, right? So let's see. Let's just draw out an arbitrary function u. Okay, and again, let's restrict our space to be the space of continuous and piecewise linear spaces, piecewise linear functions. So you would take the value of 0 at the left-hand side and take the value of whatever a is on the right side. But in between, it can take still unknown values, right? And it's piecewise linear. So we know the value of u at 0 is 0. At the first grid point inside the domain, it takes an unknown value of u1, and here it takes unknown value of u2, unknown value of u3, and the known value of a on the right side. So how do we represent that u in terms of linear combination of basis functions? Right, so how do we write u of x? In this case, what do we want to write it as a linear combination? Right, I equal to, let's say, 1 to n minus 1. Okay, so we still have u1, u2, and u3, right? So in this case, n equal to 4. So u1, u2, u3 still are unknown values. They are again multiplied with the basis functions. Oh, sorry, here are i's, not n's. Okay, ui, phi of x. But then there is a last value a. The last value a, when multiplied with the last basis function, is this function like this, right? And together with u1 times phi1, which gives me this function, u2 times phi2, which gives me this function, u3 times phi3, which gives me this function. I mean, if you add all these functions together, you get the red line, which is the function u. Okay, so that means I have to add another term, that is a times phi n of x. So this term is the new term in our representation of u because of the boundary condition. Okay, so it's easy, actually, this is easy to generalize to the case when I have a left boundary condition u0 that's not equal to 0. I would also add potentially another term on the left-hand side that takes the whatever the left boundary condition is. All right, any questions on this? So this is the only additional term I add to account for the boundary condition. All right, now let's discuss how should we modify our v correspondingly. Okay, it turns out we actually don't have to modify our v at all. Oh, this can be seen from two aspects. One aspect is that our v actually has to have however many degrees of freedom the unknown solution U has. And in this case, did we increase the degrees of freedom of our unknown U? We didn't, right? So it's just the right boundary has been fixed at a different value rather than 0. The degrees of freedom in U is exactly the same. So we don't actually have to change the space for V at all. So we actually don't add any additional term in our V. V is still an arbitrary linear combination of the 3 interior Phi's without adding anything at the end. All right. A second way to think about this is that in our energy minimization derivation, the test function V is actually a small variation on U. And a small variation on U, if U is fixed to be the value of A at the right-hand side, then a small variation actually has to take the value of 0, right, at the right boundary. So V actually, instead of satisfying a boundary condition, V1 equal to A, V actually satisfies the original boundary condition, V0 equal to V1 equal to 0, no matter what kind of a fixed boundary condition U satisfies. And because V1 equal to 0, there is no contribution from the either the first or the last basis function. So this is how we are going to be modifying the unknown and the test function in finite elements once we have a fixed boundary condition. And the only additional term is this guy, right? This is the only additional term we have.